What's up, guys? If you haven't noticed, we're in Minecraft. This is the Ore build server for people who like making things like this. Redstone, computers, contraptions, stuff like that. Uh, this is the beginnings of a computer that calculates the sine and cosine of angles using the CORDIC algorithm, which is based on shift and add stuff. This is the multiplier, which was the first thing that I built. It's 8-bit by 8-bit, so the answer is 16 bits. And it works using this wall of torches as its shift, and then having like 7 different adders. And let's just give you a demonstration of how it works. So on the bottom, we have 7. 7. It's saved in the register. On the top, let's multiply it by 5. Let's save it. 5. 7 times 5 should be 35. And what do you know? We have 32 plus 0 plus 0 plus 0 plus 2 plus 1. So 32 plus 3 is 35. So, actually earlier today I found a misplaced torch that gave me a wrong answer when multiplying 7 times 7. So you can see that this is still a work in progress. This multiplier is for the last step of the CORDIC algorithm. It's an iterative algorithm, so each time you do an iteration, there's a constant that you can multiply. But instead of multiplying it after each step, which would take a long time, you can do it at the very end and just multiply them all together. And that's what this multiplier is for. Do at the very end. If you notice these cyan things, I try to have everything color-coded, so the multiplier is all red. The cyan is a register. It's a D flip-flop, so you can save any value you want, and it's reading 5. But if you notice, if I take away these 2 torches, it still reads 5. So it's useful for when you're working with pulses, which is what basically all redstone computers are based off of. You'll notice that there's also registers over here next to the adder and over there. This adder is, it's an adder. It can add and subtract numbers. Let's give it a little demonstration. On the top, we have 12. On the bottom, we have 7. So 7 plus 12 should equal 19, which is 16 plus 3, which is true. If we want to subtract, we have to invert the bottom and invert the carry, and we should have 12 minus 7 should be 5. So this can add and subtract numbers using 2's complement. Say we wanted to store the value of 19 in a more permanent way. What we could do is we could save it to a slot in RAM. This blue, dark blue, is all RAM and has 8 slots, so 16 controls to write and read. So I have this decoder, so you can only use 4 lines of code, which is very helpful when you're dealing with small spaces and program memory. Let's save this. Let's write to the slot labeled X1, which is slot 1. So this is the write control, and this is slot 1. So if we put a torch here, you'll notice, watch this piston very closely. If you see, this piston extended, which caused a block update to this piston. And that's how this RAM works. It works on block updates. So I can take that away. And now this will stay here, even if I break this line here. This piston is not going to update unless you make it read again. So now we have the value of 19 saved in slot 1. If we want to read, then all we have to do is just place a torch here, extends this, and now you can see we're reading the same value back this way. And this reads it into the bit shifter. Now, the bit shifter has 3 segments. This one shifts by 1, this one shifts by 2, this one shifts by 4, and they're all toggleable on and off, so you can shift by any number between 1 to 7. But since the algorithm goes incrementally, you don't have to choose. You're never going to have to shift 7 after you shift 3. So what I built is copied from someone else, made this counter. And so this increments it from the values of 1 to 2 to 3 and so on all the way to 7. And so that saves a lot of time in programming, which is helpful. Another place you'll see this counter is over here. This is the read-only memory. Same style. There are 8 slots. These are all angles. What's special about these is that the tangent is always a power of 2. So this is 90. The tangent of that is infinity. 45. The tangent of that is 1. And then 1/2, 1/4, 1/8, all the way down. And that is an essential part of the CORDIC algorithm, and that's actually why you need to use the k value. It's very complicated. Just go to the Wikipedia article and you'll try to understand it. Yes, and then up here we have this pink thing. This is the conditional, and this tries to see if values are bigger or smaller. So right now we have 15 in the top, or this is actually 30 in the top, and on the bottom, let's do 4. So, since 4 is less than 15, this is off, right? Or 30. 4 is less than 30. Oh, come on. Say we have a number greater than 30, though. I keep falling down. Let's do 128. Since 128 is greater than 30, this torch is lit up. If they both had the same significant digit, this case would be 16, because, yes, right here, they have both the same significant digit. This is off, so it might tell you that the top one is greater, but what could happen is that, say the bottom was 30 and the top was 16, you'd have to rely on this subtractor and look at the last digit. If the last digit is a 1, then it's greater, and if it's not, then it's less. So it's a pretty complicated way of determining which one is less and which one is greater, and it gets confusing when you're just thinking about it, but the computer can make sense of it more than I can. That's pretty much it for this computer. The next things that I need to do is I need to make a display, and I need to make a binary to decimal converter so you can actually see what's going on and see that the sine of an angle is some decimal number. Theoretically, since this answer is 16-bit and you're never going to have anything greater than 1, so the most significant digit is actually 1, you can have answers with precision of 4 numbers after the decimal place. Theoretically, I'm not sure if that's accurate or not, because it's an 8-bit by 8-bit, so I might have to just stick to 2 digits after the decimal place to keep up, with sig figs and all that stuff. But we'll see once this computer is actually finished. It'll probably be a couple months or so. But until then, thanks for watching.